Thank you. Thank you, Saul, for that introduction. And really, the conclusion to be drawn from what you just said is I'm old. So by the time you get to be my age, you've worked on everything. First time I've ever given a talk in a bowling alley. I don't think I'm going to make much eye contact out there, but I'll give it my best. So I've put together some slides that I've been giving over the years. This is not one piece of work or one topic. It's sort of perspective. And in fact, I noticed this particular one is about almost 10 years old, and you can see, I know that because it has data science in quotes. Back in the old days, I didn't think it was real, so I just kind of say the quotes. And the quotes fell off over the years, but this slide happens to be from that era. So a little perspective. So I did look a little, I look at the videos of the previous two talks. I was out of town, but everything I'm going to say is complimentary. I agree with all of that, but there's more to say. And I think as there will be more talks in this series, the union of everything we all say is kind of what data science is. I actually don't think it's one field or one concept in the way other fields are fields. It's an umbrella term, and it's an open house for essentially everyone on campus. So I have a little perspective that I'm going to emphasize here. It's not all I work on, but I'm kind of orthogonalizing with respect to the previous two talks. It's called Gram-Schmidt, if you know what that means. So I'm going to be a little more mathy, in fact, today than I think many of the other speakers, with some apologies. You know, math talks aren't necessarily appealing to everybody. But I've honed that style over the years. I can give a math talk without many equations. And so even if you're not mathy, I hope you kind of appreciate that there is mathematical reasoning and content in this field. Very much so. In fact, there's new ideas needed. We do not have the math we need yet. So that's part of the hope I'm going to inspire here. So to me, this is a old slide, but what's new about data science isn't that there's lots of data. That's been true for a long, long time. What to me started to be really different was that there was granular data. There was data about every individual. So in the social network domain, that started to happen in sociology. And, people noted that and got excited about that. But in astronomy, you had data about every part of the sky, or in biology, you had data about every gene, and so on. So individuals became of interest. You had data about every individual, and that's a very different regime for us to be in as inferential people. We're used to making laws about aggregates. We'd collect a lot of data, we'd fit a curve of some kind, F equals ma or whatever. And now it's rather different. It's the science of individuals. It's the science and the technology of individuals. So that brings up all sorts of issues having to do with long tails. We have lots of data about some individuals and very little data about huge numbers of individuals, and we want to do a good inference for all of them. Again, this could be people, or it could be genes or proteins, or you name it. So what's challenging in this world? You need to do timely inference often. These are big data sets, and you can't just run forever. And in some scientific domains you can, and that's been the classical mode. You get a huge amount of data, you crunch forever, and you buy lots of machines. But increasingly, that's not the mode at which most people, not only in science, but especially in technology, are operating, or in medicine. You may have minutes or hours. So you can't just say, I'll crunch forever as data sets get larger and larger. It has to be transparent, has to be trustable. I happen to get a lot of T words here. And it has to be at the level of individuals. So these are challenges I think we actually don't know how to face yet. Okay? And so what's required? To me, it's not just a library of algorithms, or build big systems, or bring people together. It's brand new thinking. And so I like to use this word. I think I even coined this one, of inferential thinking. Computational thinking had been coined at NSF years ago to describe kind of the uber power of computer science. It was going to take over everything, and everything was computational thinking. And I resisted that, and so I need to kind of think of a word that countered that a little bit. I agree with it to some level, but inferential thinking is a tradition going back hundreds of years, and it has its own strength and power. To me, actually, when you bring the two together, there's where you get, that's part of what data science is. And it's a challenge to bring them together, and that's kind of part of what my talk's about. So let me say this in a very different kind of, maybe it's crazy sounding way. I'm going to emphasize the technology side. There's the science side, big data sets and all. I think you heard a great talk about that last week. But actually, maybe 10, 15 years ago, I started to hear the word data science and noted that it was really a phenomenon, really more from people in technology. They had new business models coming out based on it. And so I envisage a conversation between one of my students who's just graduated here and a boss down in Silicon Valley. Okay? And this kind of conversation really happens all the time. So the boss says, I need a big data system, whatever that means, that will replace our classic service with a personalized service. So that word personalization has been key in Silicon Valley for about a decade now. Many, many companies, that's their business model. I'm going to take search and make it personalized. I'm going to take commerce and make it personalized. Why? Because they have data about many, many of the individuals. so they can make it personalized. So my student scratches his or her head and says, okay, I think I might know. Tell me what your classic search algorithm is. Okay, it's search. There's some algorithm that takes in data, adjusts some parameters, and makes some predictions. That's probably a statistical algorithm. If you explain it to me, I can probably figure it out. And now I'll just implement it not once, but I'll implement it 100,000 times. One for each individual or maybe cluster of individuals. All right? So you just got to give me a lot more computers and some time to engineer all this, but I probably can figure out how to do that. Maybe not so hard. A big engineering challenge, but nothing more. All right, now the boss adds another caveat, which is the scalability issue in a statistical sense. So I'll get a scalability in a computer science sense here. The boss says it's got to work well for anyone and everyone. I can tolerate a few errors, but not too many dumb ones that will embarrass us. Because this is the reality of Silicon Valley, that people will build a system to serve 10,000 people, try it out and get 10,000 clients. And it's always a statistical system. There's data coming in and errors and all. So they control those errors using all the methods we know how to do. Most of those controls are based on squared errors. All right? And so you get the squared error rate down to 0.01 or 0.001 or something. And so with your 10,000 people you're serving, you're maybe getting 10 of them getting bad service. Right? And so it's not so bad. Everyone recognizes it's not going to work perfectly. Now suddenly your business really goes well. 100 million people suddenly are on your site because it's so cool and successful. And suddenly that 0.001 doesn't look very good anymore. Suddenly you've got 10,000 people being served badly. And I've seen companies where this has happened, where they go through that thing and suddenly it's awful. And now those 10,000 people start writing to the newspaper or wherever, posting, tweeting or whatever, and everyone talks about how bad this company is, and they die. Okay? So people in Silicon Valley are very aware of this dynamic. So how do you fix that? Well, you have to be a better statistician. You can't just worry about L2, about squared norms and variances. You have to worry about tails of distributions, and that's engineering. That's hard work, and it's math. All right? So my student's sitting there saying, well, scratching his head even more, saying, I'm not sure I was taught how to do that at Berkeley, but I think I could try to figure it out, and I'll work hard, and maybe it'll work. But now we're more in the realm of maybe. It's not engineering thinking at this point. It's let's try it out and see if it works. But it only gets worse, and here's where it really gets to me conceptually interesting. Boss also says, very natural thing, it should run just as fast as our classic service. Why? Well, that's part of it, has to be, because that's the business plan. So if you were around in the 90s when Google came around, you may remember search engines before that. You would type in a query, you'd hit a button, and you'd wait for a few seconds, maybe 10 seconds. And it really was not good. It interrupted your flow of your thinking. Suddenly Google is available. Not only was the search hard quality, but you hit your button, and within 1 or 2 seconds, you always got an answer. They engineered that to death, and it really worked. And now all of us expect that. All right? So suddenly you're building now not just a single search engine with one algorithm that you have to kind of shard and replicate and all that. You have to have 100,000 different models that are individualized and have the right one sent to the right person at the right time for the right purpose. There's a heck of a lot of engineering having to go on, and you have to do all that within 2 seconds. It can't slow down, because if someone hits a button, even though you're telling them, I'm giving you a better service, it's personalized, if they have to wait 10 seconds again, you're dead. You can't do it. All right? So now we really have the computer science coming into play. Run as fast as, that's a computer science statement. That's a runtime requirement. It's a constraint on your statistical algorithm. And it says we don't have constraints of that form. We don't have runtime constraints on our algorithms. We never have. We need them, but the theory and the practice has not had the notion of runtime. You can look for in vain throughout the entire statistical literature and not find the word runtime. Okay, maybe in the results section or something, but it's not the focus. So my student really is now at a loss. Okay? He or she sits there and says, I don't think I can do this, but I'll try, and if it's not running fast enough, just buy a whole lot more computers and maybe it'll start to work. And again, this may sound fanciful, but this is reality of Silicon Valley. A lot of companies will try this until they spend all their money, and then they will maybe die, or maybe they'll make it. But it's all just ad hoc. All right, now it gets to me, here's the one where as an intellectual I really start to perk up. It should only improve as we collect more data. In particular, it should never slow down. So over the next 10 years, all right, I'm going to go from a terabyte of data, I'm going to get a petabyte of data. I'm going to have much more data about each individual. So I should be able to provide a better and better service over all that time. I'm getting more of what I need, the data, right? But it should never slow down. That means as you go bigger and bigger, as you scale in size of data, it can't slow down. But all of our algorithms, they're n log n, or they're n squared, or they're n cubed, or maybe log n, but they're not constant. Right? So we don't have algorithms that permit that to happen. Okay? So now you have to think about very ad hoc mechanisms of, well, I'll just do it in parallel a whole lot, and hopefully it'll work. Or I'll subsample, and maybe I'll give bad service now to some people, but I can't help it. All right, so that's where we are. All right, and then of course the boss says there's other things too. You have to worry about where the data came from. There's privacy concerns, all kinds of legal issues. You have to take that into account in designing the system. All right, so my student probably runs out of the room, hair on fire at this point, say no way. But this is really a problem in some sense. So if this is just search or commerce, it's maybe not such a problem. But if this is like someone's built a big medical decision-making system that helps all of us to take in our genomes and give us advice on what medicine to take or what operations to have, or if it's the financial system, or if it's the transportation system, and that's where we're heading. So I like to describe this as a situation of like 3,000 years ago, people were starting to learn how to build buildings and bridges. And people did pretty good. There were some bridges built, some buildings built, economies prospered, and great things happened. But it was all ad hoc, and it was word of mouth, and it was a lot of people died. A lot of bridges fell down, a lot of buildings fell down. And eventually a field emerged called civil engineering. And civil engineering was, I can give you certain guarantees. So this kind of soil, this kind of wind, this kind of structure, and so on. I can guarantee under certain conditions they won't fall down. All right? So you see people in the hurricanes, they're up in these buildings which are hurricane-proof, because you can do that. All right? We don't have anything like civil engineering for this field of data science. Okay? Nothing like it. So people build things and hope. So that's okay for things like search or advertisement placement and all that. People get bad advertisement placement and they just complain or whatever, don't look at it. But it's really a problem when we start thinking of this as all of everything in our infrastructure, all of our science, all of our technology, everywhere our human serving computers are doing this. So people are talking a lot about the peril of AI these days and superhuman blah, blah, blah. That's all nonsense. We're not going to get superhuman intelligence in our lifetimes, not even close. But we are going to get bad systems that don't work well because they're making tons of decisions that they're not equipped to make, and they're not scaling well, and no one's thought about these issues. Okay? So to me, that's a good part of the problem that we need to work on as a group, really. It's not just technical, it's sociological as well. Okay, so I think of one way to getting started on this is you have to combine two styles of thinking, inferential and computational. Computational really just means take a good class in computer science where you learn about modularity, abstraction, scalability, absolutely, and robustness and so on. Not just how to program. You need to learn the way to think. All right? But inferential thinking is just as powerful. You have to learn how to do this. You have to always consider not just the data, but what gave rise to the data. All right? Not just process the data. That's not inferential thinking. You have to think about the sampling pattern that gave rise to the data. Otherwise, you're going to say the wrong things about what's out in the world. And you have to think about going backwards. So statistics is fundamentally an inverse problem. And the mathematics of inverse problems is challenging. And so some of the problems I'm alluding to, it's because we don't know how to solve them because we can't do the inverse problem. So let me just say this one more time and kind of get more philosophical language. But there is a core theory in computer science. It's some version of complexity theory. Turing and others, Kolmogorov developed it. And in statistics, there's a core theory. It's called statistical decision theory, both Bayesian and frequentist. If you look in core statistical decision theory, you will not find the word runtime. It's just not a concept in the theory. Okay? You can't trade off runtime against amount of data or dimensionality or complexity and so on. It's just not in the equations. And similarly, in computer science, you won't look in vain in complexity theory for the statistical risk, which is an expectation of a loss. Okay? It's not there. You will find worst case bounds of all kinds, but not expectation of a loss function, which is what, as an economist or a statistician, you have to have. It's fundamental. You need to trade that off against other things like runtime or memory or energy and so on. So these two fields, although you can try to link them up in various ad hoc ways, they don't link easily. And even worse, if you look at the lower bounds in statistics, where you start to get real fundamental understanding, there are lots of lower bounds, and they really are quite far from runtime. They're just for any algorithm, blah, blah, blah. And in computer science, there are very few lower bounds, and the ones they are very far from the upper bounds. So it's a field which is it's still immature in that sense. It hasn't really started to tighten up its fundamental understanding. So there's huge gaps here, and people with kind of mathematical minds, the Kolmogorovs and the Turings, are going to be needed to start to figure out the new concepts we need to do computing, which is statistics and inferential oriented. No one's thought about that. I mean, Kolmogorov thought about that, but then the field's kind of split apart. The computer scientists went their way, and the inferential people went a different way. So I think it's all about bringing it back together. So here's an outline in my time what I'm going to try to do. So I'm going to race a little bit. Part of the point here is to give you an idea of things we work on and not all the details. Most of this work is over the last 5 years, so there's lots written about it. But I'm going to talk a little bit about privacy just because I think it's an easy way that I can sort of give the feeling of how you bring a computational and a statistical idea together. I think I'm going to skip the second one like a time, and I'm going to spend maybe 20 minutes on this part, which is some math. But it's math that's very familiar to chemists and physicists and mathematicians, and it's highly relevant to this field, somewhat surprisingly. And so I do want to get there, even if you're not mathematical. I think you'll find that intriguing. So this is with John Ducci and Martin Wainwright, colleagues here at John's now at Stanford, and Martin's here at Berkeley. So this is a problem that I think you're all aware of, that when you have data, you can't just assume you can use the data willy-nilly. It's personal data often, and people should have control on how much it's used and how much privacy loss they will incur. You can't just say, yes, no, you can have my data or not. That's kind of the legal perspective, our current legal perspective. You want to say, well, I'll lose a little privacy if you use my data, but if you give me enough money, that's okay with me. I mean, that sounds stupid, but that's real. If you want my genome, I'm not going to give it to you, but maybe if you're using it to study a disease that runs in my family, that's good, because as a utility, that's good for me. Or maybe if you give me $3 billion, I'll give you my genome, because that's good for me too. So there's always a trade-off, and we have to expose those trade-offs. So we want to trade off privacy loss against the value we obtain from the data. And you can't just, that has to be quantified. So you have to be a statistician. You have to have a concept of risk. That is the value you obtain from the data. So we want to trade off risk and privacy. Okay? So let me just show this in pictorial form. Here's a classical database person's way of thinking. So I'm going to be a computer scientist for a minute. No stat. So I have a database which contains data, say banking data. So I've got a bunch of people. I've got their age, their height, their weight, their address, and I got how much money they have in the bank. So classical banking data. And I put a query in, like who has the maximal amount, or what's the average, or something. And out comes an answer, which I'm going to call, weirdly, theta twiddle. All right? Now, there exists a field called differential privacy, and there's other privacy formalisms that are able to do something very nice. They can take a database, they can add noise to it in some sense, fuzz it up, give you a privatized database, where you can put in the same query, and you will get out an answer which is provably close to theta twiddle over all queries and over all databases and with high probability over Q. So that kind of statement, that kind of theorem exists. Okay? So that's very nice. So it looks kind of statistical because there's a stochastic operator in here and so on. And when I first sort of learned about this, I would ask my colleagues working on this, well, are you able to do inference? They'd say, well, sure, because the query could be, calculate a median or mean. Isn't that inference? Or do a linear regression. I'd say, no, that's just descriptive statistics. It's not inference. And they'd say, what are you talking about? All right? And that's when I kind of realized that I needed a buzzword, inferential thinking, to sort of say what I meant. And I'm going to now have it as a picture. So here's what you do in statistics. You take your database, but you don't think about just the data in the database, like the banking data. Okay? You think about where the data came from. Now, for banking data, that's not reasonable. The computer science way to think is natural. You only care about the people in the bank. You don't care about people who could have been in the bank but decided not to be in your bank. All right? But now think about a medical problem. I collected a bunch of medical data. I got a bunch of people. I got their age, their height, or weight, and I got how long they lived after I gave them a drug or not. Treatment control. All right? Now, do I care just about the people in that data set? No. I care about all the other people who could have been in that data set. In fact, the people in the data set could be dead and gone. But I collected the data so I can use it to predict for someone who could have been in the data but wasn't, i.e. the next person who comes into the doctor's office, whether I should give them the treatment or the control. Okay? So that is a very clear example of an inferential problem. I don't care about the data at all. I care about what's. So how do you set that up? Well, you say there's a population of people who could have been in the database but weren't. There was a selection mechanism that picked the particular people in the database. And I could put the same query into the population as I put it into the database, meaning I'm asking for someone in the future or someone who wasn't in the database, and I can get out an answer. And what statistics does as a field is looks at this setup over many various kinds of problems and proves that theta twiddle is close to theta with high probability over S and with over all queries and over all P. There's theorems like that exist. Okay? 100 years of theorems like that. And now I hope you see where I'm going. I want to put the two together. Okay? And this has not been done, mostly. I want to say, look, I gathered the data to do medical stuff, so I have a database of people I gather data from, and I got to make some guarantees to them, and I'm not going to just show their data. I'm going to privatize. So I will privatize. Even if they're dead and gone, their children might care. So I have a contract. I will privatize. All right? And I'll put queries into the privatized database. I'm not allowed to put queries into the real database. All right? And I will now prove that theta hat is close to theta. I don't care about theta twiddle at all, with high probability over all S and Q, and over all queries and over all populations P. So my colleagues and I, Martin and John, we worked on this. We have such theory, and I'm going to briefly show you what it is. We have a bunch of long papers on this. But the main point here is that you can do this, and this is what you really want. Okay? You have to solve these problems together. So here's just an example of us trying to do this. Let's imagine we have n people who hold data privately. They don't want to reveal it, but they will put it through a channel, which in some sense adds noise, and they're willing to reveal the z values to a statistician. Maybe the further guarantees are needed, but they're willing to at least do that. All right? So based on z values, I want to make inference, even though x I would have loved to have had, but I didn't. All right, now here's one equation. Here's one slide that has math on it, but just I need to show you. We turned this into a minimax problem, an optimization problem. All right, so we took a loss function, which took the truth, compared it to the estimator. You want that to be small. We took an expectation over all the randomness, the sampling of the population, and the channel, which added differential privacy noise. All right. We took then the best procedure, that's the minimum, over the worst case probability distribution to cover every possible eventuality. And here's the new part. That's all classical. That goes back to the 30s. That's walled. The new part is just the green part, which is we took a further infimum over all channels which protect differential privacy to level alpha. That's a quantifiable statement, and now that's a quantifiable optimization problem. All right, and so we did the math on this. It's basically empirical process theory and covering numbers and some information theory. And we were able to solve this problem on lots of interesting situations. So let me show you an example. Here's data where people abuse substances. This particular person abuses alcohol and cocaine and not the others. And in some city, imagine the underlying proportions are these. 45% of people abuse alcohol and so on. These seem a little high to me, but whatever. I made them up. Now, I would love to have I know this is the truth out in the world, in the population. If I knew those, I would know how many hospitals to build, how many doctors to put. I could do public policy, right? But I don't know those, so I try to infer it from data like this. Now, when I have data like this, I can just take sample proportions. That's called the maximum likelihood estimator. And I can estimate these uniformly well. But no one wants to reveal that kind of data. Okay. So back to that math. If I just solve that minimax problem without the green part, I get a rate for how well I can estimate those proportions from that kind of data. And it's a classical rate. It's the 1 over square root of n rate. As I get more, that's the amount of data, n. As I get more and more data, the accuracy gets better and better. It goes down at rate 1 over square root of n. All right, so that kind of, there's hundreds of thousands of paper statistics that give you rates for different kinds of problems. I picked one problem here. Right, what if we now do the further infimum over the green part? We should get the parameter alpha out of differential privacy, if you know what that is, appearing in this equation somehow when we do the math. And so we did, and here it is. And it turns out this happens in essentially every problem we've looked at. So we think of this as a law of private data analysis, to give it its due. You do is you take the differential privacy parameter, alpha, and you square it and multiply it by n. So the effective sample size was n, now becomes n alpha squared. And so let me briefly tell you what alpha is. It's a parameter which if it's small, if it's 0, then I take whatever the data was and I completely randomize it. There's nothing you can say about it anymore. You're completely private, but you can do nothing with it. And as alpha gets larger, if it goes off to infinity, no privacy. And so it's a knob that someone can turn. It's a bit of currency they can turn. And people, I think, over time will get used to what it means to have an alpha of 0.5. And they'll relate to money or their feelings. Okay? So 0.5 is actually not a bad number. Let's imagine I ask Kim, can I have your genome? And she says, well, what problem are you trying to solve? I said, disease arose in your family. She says, okay, I'm comfortable with alpha at 0.5 for that. I'll lose a little, you'll learn a little bit about me, but not too much. All right? And so I say, okay, I made a contract. And then I square alpha, I get 0.25. I multiply that by n, and I realize if I'm getting data from people like Kim, I just got to get 4 times as much data, and I will have the same risk as I would have had with the pure data. And that's the cost I pay to be private, to allow privacy, just 4 times as much. And I knew that before I collected the data. So this is the civil engineering of data science. This is something a civil engineer needs to know. What's the rule of thumb for how much data to collect so I can make a guarantee and get good risk? All right, and so that's not ad hoc. That's a real theorem. This happens for lots of other problems. Let me just sort of compare this to what's out there in the literature. The standard thing to do, Dwork et al. As an example, is to add what's called Laplace noise to data. Laplace noise is heavy-tailed, and it really fuzzes up the data a lot. All right? If you add Laplace noise, that's fine. You do protect differential privacy at level alpha. The contract is golden. right? But you might hurt the data so much that you have a bad risk. You're not doing good statistics with it, all right? So in fact, that's what happens, it turns out. That's not a good mechanism. Here's a better mechanism. In fact, this is the optimal mechanism, because our theory gives us this equation. And if we achieve that equation, we're optimal by definition. So here's the new, or it's a different, it's not new actually. You take your private data, someone abused alcohol and cocaine and not some others, and now you define two random bit vectors, v and 1 minus v, all right? Drawn uniformly, just random. And now you send to the statistician the closer of v or 1 minus v with probability that's a function of alpha, right? So you're not going to understand that right away, but just let me assure you that guarantees differential privacy. And it seems weaker. It's not just adding noise to data. It's really taking totally noisy data and transmitting one piece of noisy data or another piece of noisy data. And the only information that's being leaked is this closeness. But it turns out that this protects privacy and it's the optimal risk. And so we did this with real data. This is drug abuse warning network data. Sample size is up to 60,000. This is this stringent L infinity error I alluded to earlier, not L2. And the add Laplace noise is that green curve, very bad risk. This is on a log scale. And this other mechanism, which is really randomized response. It's actually an old idea. The optimal mechanism is way better. So this is what I would do in practice. I would suggest doing this mechanism instead of adding Laplace noise if you're trying to preserve the data for the purposes of inference. OK, so that was a little vignette. I could go on, but I won't. Let me turn to the last or second part of the talk. So that was how do you trade off statistical risk against privacy? Because you have to trade them off. You can't just say one or the other, right? That's kind of where we are right now. As many of you know, you can't just send genomes around at all. You're completely blocked right now because there's the privacy leakage. Well, you'd like to be able to send it a little, right? So you have to trade them off. So what other kind of trade-offs can we talk about? Well, you can talk about trade-offs of risk and compression. If we have huge data sets, you can't send the entire data set. You have to compress it. Classical Shannon theory says here's how you compress just for transmission purposes. But that theory can have you compress the data in ways that ruin it for inference. So you can set up the same exact kind of problem, take an infimum over all channels that have a certain bit constraint, but still give you good minimax risk. All right, and we have papers on that as well. So you can keep going. You can have other externalities. I think of these as externalities. You can say risk plus some other externality. And there's still much to do along those lines. So but the mother of all externalities is computation. I'd like to say risk, but with good control of my computation. I want to trade off computation against risk. If I have to make a really fast decision because it's being demanded of me, I'm going to have a higher risk. If I can take more time, I'm going to have a lower risk. And I want to be able to control that in a medical domain, a transportation, or a finance domain. All statistical inference problems have a temporal budget. All right? If you're in the finance world, it's microseconds. You cannot wait more than microseconds because you're dead in the water. In the search and online advertising world, it's milliseconds. And in the self-driving car world, it's going to be seconds at best. You're using inference problems. What's out there? What control signal apply? In the medical world, it might be hours, but every one of them does. Very few problems are like the statisticians of the past, where we get the data set, you give me a year, I come back with some error bars, and you're happy, we publish. That's still alive, but it's not really where the main thrust of the field is. Okay, so how do we do it? Well, we have to have a way to trade out. What we'd like to do is take the infimum over all computational mechanisms with some resource bound of the minimax risk. That's impossible. No one knows how to do it. Turing theory does not tell us how to do that. Okay? It's not a well-defined set, this set of all computational mechanisms that meet a resource bound. So given that fact that some of us are aware of, and we've been struggling with it, we're trying to come up with a new theory. Turing theory got us a certain distance, but it's not adequate. It's not the right one for this field. Come up with other approaches to this problem. I'm going to just say I think this is hard, and I don't think we know how to do it. So for the young people in the room, if you want a millennial challenge, this is it. So in my group over the last 10 years, we've been trying all sorts of things, and we've had progress. We've solved some little minor problems, if you will, with some geometry, some concurrency control, some optimization, and subsampling, and so on. So using all kinds of ideas and trying things out. And it's been very, very fun and useful. But we don't have the big mother solution at this point. But I'm going to tell you about the one I find the most, at least, elegant at this point. So I'm going to talk about number 3, optimization oracles. So the dirty little secret of this field is that it's not actually computer science theory, complexity theory, that's been helping and drive this field forward. It's been optimization. Okay, so optimization is a computational model. It says, given a certain function and given a certain number of steps, that's the computational time, here's a certain accuracy I can deliver. That's a simple computational model. And they're, amazingly, and I think this is so amazingly not very well known, they actually have lower bounds. There's a notion of the best optimization algorithm for a certain problem. In some ways, the optimal way to optimize. Right? Very few fields have that, but they have it, and it's this Russian school that did this about 40 years ago. And in optimization, everyone knows about this. But outside, people don't know about it. They just know about conjugate gradient and Newton's method and so on. They don't know that those are just algorithms that have a certain runtime. There actually are lower bounds, and there's some algorithms that achieve those lower bounds. Okay? So if we're interested in fundamentals and how to trade off statistical concepts against computation, we want to look at those lower bounds. Those are computational lower bounds, and see how they match up to statistics. Right? So we haven't, again, solved this, but we've made a lot of progress. So this is where some physics comes in. So it turns out that, surprise, surprise, to understand these kind of ideas in optimization, you have to go into continuous time. Optimization is almost always, it's really always been done in discrete time. And I think that people thought that was without loss of generality. That's just dead wrong. So in this last little part of my talk, I want to show you going to continuous, energetic kind of ideas is a way to understand optimization more deeply. So I really want to acknowledge three really outstanding collaborators here: Andrew Wibisono, Aisha Wilson, working with me here at Berkeley, and Mike Betancourt we brought in on the last phase of this. He's an expert on symplectic integrators from Columbia. Okay, so let me step back a little bit. Just as I alluded to, in data science, optimization plays a very, but increasingly important role. It supplies algorithms. We use them all the time. But it supplies lower bounds, and thereby fundamental understanding. But I'm going to argue that perhaps surprisingly, it's still an immature field, even though it's probably hundreds of years old. And open problems abound when you start trying to do optimization in some of these novel settings. Okay? They're unanswered questions. And I think by solving some of these, we're going to make progress on these bigger problems that I've been alluding to. Okay, so let me again step really far back. If you look at the more mature fields, the mathematically inclined fields, they have an interplay between taking derivatives and taking integrals. You kind of go back and forth between those two perspectives all the time. So certainly physics with Lagrangian and Hamiltonian perspectives is a great example of this. Statistics also has lots of that. There's Laplace expansions, saddle point expansions, which are kind of little bits of applied math where you, to do integrals, you take derivatives. And so lots of that. Also the numerical disciplines. Finite element analysis is a variational discipline. It turns a PDE into an integral. Monte Carlo, similar kind of things. Hamiltonian Monte Carlo, and so on. Optimization, surprisingly, if you pick up books or papers on optimization, all you see is derivatives. Hessians, gradients, you name it. You never see an integral sign. Maybe a Taylor expansion or something, but that's it. It's really it's shocking. Okay, so now let me just tell you what I'm going to get to in the last 10 minutes or whatever I've here. So this is something that very few people seem to know about outside of little niches. At Berkeley, there's some niches which know it extremely well. I knew it a little bit back when I was a professor at MIT, but I never used these ideas. And suddenly, last year, I realized that they were relevant. So forget about everything I've been talking about. Let's just consider that we're doing physics or chemistry. We have the equations of the cosmos, or the equations of a protein. All right, and it's a differential equation, maybe PDE. And we want to solve those. All right, now if you were to solve them exactly, you get these flows. And you would, these flows have various properties. They conserve quantities like energy, momentum. There's a whole exterior forms algebra, which is developed to kind of express these ideas more generally. So they conserve various quantities. And now if you say, well, I can't solve these, it's nonlinear and complicated, I have to put it on a computer, you have to discretize these differential equations. So you could just discretize in a naive way, Runge-Kutta or whatever, and you will get not the flow, you'll get something that's kind of nearby. Right? But the problem could be that as you're hopping along there, you're also not conserving energy or momentum. So the whole thing is running, you're a simulation of the cosmos, and it's approximate, that I have to accept, but I'm bleeding away energy or momentum. I'm not doing the right physics anymore. All right? So pretty amazingly, this was realized by people in the late 1800s. So Hamilton, Jacobi, Poincaré, they realized this was an issue. And they said, is there a mathematical framework which allows you to discretize differential equations while still conserving energy, momentum, and various other first integrals? And it turns out there is, and they developed it, and it's a beautiful theory that's extended to this day. I think at Berkeley there's been many contributions to this theory, still to this day. So the answer is yes. And so this seems completely unrelated to optimization and everything I've been talking about, but I'm going to show you it's intimately related. All right, so last little bit here. Let me worry about my time. So, Saul, do you want to tell me? Okay, so I'm good. So let's go to something extremely simple. We're going to take a convex function f, and we're going to try to minimize it. Okay? So that's a tractable problem, and there are many algorithms that will do that. If I'm just going to allow myself a very simple calculation, I can't expect to be able to do Hessians in lots of modern data analysis problems. I'm just going to allow myself to do gradients. All right? So I might do gradient descent. There it is. Hopefully all of you know about that. Now, you can ask about how fast does that converge to the optimum? And that's an interesting already math kind of question. It sounds like it depends on the function. If I had a totally flat function, I'm at the optimum in the very beginning. Right? If I have a function that goes like this, I can be there quickly. But if you ask, what rate do I achieve over all possible functions, it's not terrible. It's 1 over k. So that was proved maybe only about 30 years ago. Okay, and it's not a hard proof. So there's an algorithm, and there's a convergence rate. And there are other algorithms that also only use gradients, and they have a certain convergence rate, and these have all been analyzed at this point. At some point, someone came around and asked, well, what's the best you can do? And that someone is named Arkady Nemirovsky, a real hero in optimization, a hero of mine. He had his 70th birthday recently, and I got to give a talk there in Georgia. He immigrated from the Soviet Union and just an amazing person. He asked, can I have a complexity theory? Given it's a convex function, and only that, smooth, and given that I can only see gradients, and given that my algorithm is restricted to take the next step within the linear span of all previous gradients, gradient descent does that, so I need some restriction. I can't just have an arbitrary oracle that can do anything. Given all that, he was able to prove that there's a lower bound. There's a best way to optimize, and that lower bound is 1 over k squared. So it's faster than 1 over k. So people had, for a long time, thought that algorithm was optimal if you could only look at gradients, because it's the steepest descent. It's doing the best thing you can possibly do right in this moment. And unbelievably, that's not. So for a while, there was an open problem. Is there an algorithm which achieves 1 over k squared that just uses gradients? All right? And another hero of the modern era named Nestorov, Yuri Nestorov, also in that Russian school who immigrated, this time to Belgium, came up with such an algorithm. So this goes back to Newton. This is 30 years old. It's just 2 equations, not just one. The first, you introduce a new variable y. Y does a gradient step, and then x is a combination of the last 2 values of y. So it has a flavor of momentum or heavy ball or whatever. Those intuitions are all fine. They don't really work in general. But the amazing thing is this is faster than gradient descent. Also, it's amazing that this thing will go down for a while, then it'll come back up. And that seems just implausible. If you come back up and you're trying to get down as fast as possible, but that's correct. You have to go up to get fast. Okay, so that was done in the 80s. And again, people in optimization know this, but people outside aren't aware. It's really it's pretty amazing. So in the meantime, people were trying to figure this out. They said, well, can we try this for other algorithms, not just gradient descent? So they looked at all the other algorithms that mirror descent, cubic resolution, and this goes on. There's like 1,000 of them. They all had a classical theory. They were well understood. And they accelerated every one of them. And they got the faster rates, and they met these oracle lower bounds. So the field really was making progress. The problem was no one understood any of this. Right? These were just some algebraic manipulations that one did that take pages. And then the proof of convergence was yet more pages, and it was completely opaque. Okay? Completely is too strong. I mean, Nestorov understood it, but it was not easy. All right? Okay, so now you can ask, is there a way to think about this stuff? Is there a notion of acceleration? Is there a notion of the optimal way to optimize? Is there really a meaning to a lower bound? All right? And if you think about all this literature, it's all done in discrete time, where you're hopping between points. The notion of acceleration feels like an infinitesimal notion. Right? It's hard to kind of talk about hopping between points and accelerate. All right. So let's go to continuous time. Gradient descent is a discretization of a very famous mathematical object called gradient flow. That's just a differential equation, takes a gradient and flows along it. If you discretize that in a naive way, you get gradient descent. And mathematicians to this day are still writing textbooks on analyzing gradient flow. It's a beautiful, amazing field. has convergence rates, has all sorts of things. A very nice paper came out in 2014, Suba and Coinez at Stanford. They took those two equations of Nesterov and they took the step size to 0, thereby turning it into a differential equation. When they did, that differential equation popped out. If you rediscretize, you get the Nesterov equation. All right? So this has, and then they analyzed this thing and showed it had the fast rate of 1 over t squared. So in continuous time, they were getting this faster algorithm. It's funny. Why is there a 3 there? Well, it has a damping, but it's a funny damping, and so there's a lot of mystery about it. But this was enough for us to trigger our thinking in this regard. We said, well, differential equations, where do they come from? If you have any physics training at all, you don't just accept a differential equation. You say, what's the energy, the Lagrangian or Hamiltonian behind that differential equation? All right, so we set out to do that, and that's what I'm going to tell you about in this last little bit. At the very top is the thing we eventually discovered. Okay, we call this the Bregman Lagrangian, so I'm not going to build up to it. I'm just going to show you what it is. Forget all these little time scalings, the gammas and alphas and betas. Those just give us degrees of freedom to have a space of algorithms. Those aren't the important part. The important part is that first term, which is called a Bregman Divergence. I'll show you in the next slide what that is. And the second term is like a potential energy. It's the function you're trying to go downhill on. Okay? So I'll explain this a little bit more in a minute. And if you're not mathematical, don't worry. I'm going to sort of wave my hands enough so you'll kind of understand what we're trying to do here. This is like a Lagrangian. It has a kinetic energy minus a potential energy. And you may know in physics that that's the kind of thing you want to go downhill on. Okay? Not just a potential energy. You want these two together. Okay? And how do you do the actual math? Well, Lagrange and others worked this out. They took that object, that time-varying object at the top, they put it inside of an integral, and they found the curve which minimized that total integral, the action. Okay, so the dotted curve might not optimize it, the solid curve might optimize it. And this is, you solve this with calculus variations, extension of calculus to allow infinite dimensional systems, and out pops this, well, not out pops, the theorem is that you just hit that thing there with some partial derivatives and hit it with a time derivative, and this gives you a differential equation. So we're now going back and forth between integrals and differential equations. Okay? So as you all know, Newton wrote physics down with differential equations. F equals ma is a differential equations. Lagrange came around 100 years later, some historian here can help me, and said, I can rewrite all that with integrals. And this is what he did. All right? And I've given this talk a few times in Italy and France, and I love to say that Lagrange, by the way, despite the name, was an Italian. And I'm an Italian citizen, actually, and I'm proud of to be in the same stock that Giuseppe Lagrangia was from. So there it is. So what is this first object here, this Bregman divergence? Well, it is a generalized distance measure where you have an auxiliary function h, which reflects some of the geometry of the problem, roughly. And if I'm trying to measure the distance between x and y, I take a linear approximation to h, and I take the discrepancy between the linear part and the nonlinear part. So that red distance measures the distance between x and y in this direction using the auxiliary function. If that h function is the quadratic, this is just a fancy way to say Euclidean distance. All right? So our Bregman divergence is a kind of where you are x, and you measure using this fancy distance kind of a little bit ahead. It's a look-ahead scheme. You take x plus a time function times x dot. So it's a little bit of stretch or elasticity in some direction. All right? And if, in fact, if we put h in there, it reduces to that form, 1/2 x dot squared, which is a very familiar term to a physicist. That's the kinetic energy. And so the second term could be called a potential energy, and this really is a Lagrangian. All right, so back to this Euler-Lagrange equation. When we do that, we hit this equation with this mathematics. Out pops this master differential equation. So this is kind of the last bit of math, with apologies with some math, but there is a master differential equation. That one actually captures all the known, at least all the ones I know, all the known accelerated methods, okay, including Nesterov's and all the others I listed. Okay, so it's different choices of alphas, betas, and this geometry factor h. Okay, so now what did we learn from doing all that? We cast a problem into continuous time. Well, it turns out that you can now ask about the convergence rate of that continuous time differential equation. Most convergence rates, as I alluded to, are pages of math, and they're specialized to particular problems. Here we can get one convergence rate for all of them with a one-line proof. And there's the proof. You write down what's called the Lyapunov function. You take its first derivative. You ask that first derivative be negative. To achieve that, you need that convergence rate. Okay, so that would set us to feeling pretty good about being on the right track. Somehow we'd capture somehow this problem. All right. Now the next little step is a little, it took time, but, and I'm going to need to describe it in English, I think. So we have this master differential equation. It has a fast convergence rate. In continuous time, it seems like we've actually explained acceleration. All right? And in fact, it turns out that in continuous time, the acceleration is not an interesting phenomenon at all. Right? If Saul chooses a particular a clock speed, and he writes down that differential equation using that notion of time, he will get a particular algorithm that goes along a particular curve at a particular rate. And he'll get from A to B at a certain amount of time. Okay? If I choose a different clock, I can set up the same set of equations. And these equations are covariant, meaning that I will follow the same exact path that Saul followed, right, but just at a faster speed. Right? If someone else, Kim, chooses a different clock, she can go at an exponentially fast clock. She loves to really go zoom along. It turns out she will have to follow that same curve, but she will zoom along. All right? So it's like Einstein. The clocks don't matter. None of this is all that important. What's important is that they all follow the same path. So in that sense, we've discovered an optimal way to optimize. All right, now here's the last part of the mystery. I'm going to skip over some slides. It says it on these slides, but I'm sensing I want to kind of get near the end. All right, so here's the mystery at this last little stage here. All right, so in continuous time, you can go as fast as you want. All right, you can define your own clock, which goes super fast. All right, but now we have this in continuous time thing, but we want to have to put this back on the computer so we can have real algorithms that people can use. Okay, so somehow Saul's algorithm, which has a certain speed, you can discretize it and get an algorithm. Mine you can, but when you go to this exponentially fast person over there, something breaks. Because we know we can't get exponentially fast convergence back in discrete time. All right, so that seemed to be a mystery for a while. And so also what happens when we arrive at that clock speed? How will we know that we're at a clock speed that's too ambitious? What breaks? Is there a phase transition somehow? It turns out there is. And then once we've realized we're on the right side where we can discretize, how do we do it? Because a slide I skipped there shows that if you just naively discretize these equations with Runge-Kutta, they're unstable. So these are very interesting differential equations. All right, so I'm set up for the last couple of minutes now. The answers are to be found in symplectic integration. Okay, so this technique, which was developed for something completely unrelated, turns out to give you answers to all three of those equations, all three of those questions. All right, so let me just say what a symplectic integrator is at this point. We have a differential equation. It's just how do you discretize? That seems like a banal question. But as Hamilton and Jacobi and others kind of realized, that's not at all banal. That's where all the math is. And answering this question of what's the optimal way to optimize, that actually is the question. All right. So symplectic integrators, roughly speaking, here's the short version. If you take a simple differential equation, you can do what's called explicit Euler. All right, where you take your current state, you add a derivative, and that tells you how to move to your next state. All right. Or you can do what's called implicit Euler, where you evaluate the derivative ahead in the future. All right? Okay? And that gets you a little system of equations you have to invert. A little more work, but often better convergence. Neither of those conserve energy or momentum all by themselves. If you interlace them, that's symplectic. Okay? So this was early on realized by the Jacobis and Hamiltons, and it's led to a whole huge literature where people have found all kinds of interesting interlacing schemes. And if you look back at those Nesterov equations that I showed up there, hidden inside of those is this interlacing. And that's when we finally realized that we realized that this had to be symplectic. Right? Now so now let me show you, here we go. So we've done it now. Here is symplectic integration of, not the Lagrangian, we ended up working in the Hamiltonian formulation. There it is, it's beautiful, it integrates, it's stable, and that rate there is exactly the theoretical rate. All right? So this really does work, off the shelf. And it oscillates in predictable ways. We've now completely understood it. All right? But here was here's my last little bit. If you now compare that to the Nesterov method, which is this existing method that he came up with in his own brilliant, genius way, not with this machinery, it also achieves that rate. We know it does. But near the end, it's better than ours. Okay? All right, so what's happening here is that as you're trying to optimize a complicated function, I've been talking about convex, but this all goes true for non-convex too. As you're way far from the optimum, it's good to build up a lot of momentum and careen down as fast as you can and go around the curves and going up and down and all that. As you get near the end, you don't want to have all that energy and momentum built up. You want to slow down and go really fast to the optimum. Gradient descent does that for you. Right? Now, if you're trying to go down at the bottom, you never converge. You just kind of keep hopping around. That's like Monte Carlo. And that's what Hamilton Monte Carlo does. Right? But somehow optimization needs some new ideas. We need to have a blend of the momentum sort of ideas and the gradient ideas. So we've ad hoc done that. We blended the two. And here's what the mix does. It's achieving the asymptotic oracle rate, and then it's really good at the end. Okay? And this mix is just as good as Nesterov. All right? So at this point, we have something fairly satisfying we can publish because we have a method which is as good as the 40-year-old champion method. But we had and his was in some sense really ad hoc. Ours is less ad hoc, but there's still some ad hocery in it. Okay? So I hope you sort of see that we're excited because how do we get rid of that last bit of ad hocery? That's going to require some deep thinking about what does it mean to optimize? What's the best way to optimize? What are the principles, the symmetries, or the, I mean, after Lagrange, I think it took 100 years, I have to ask the physicists, for people to realize why is the Lagrangian the right object to study? Because it had certain mathematical properties. And so I think we're really at the onset of this problem. All right, and if you agree that's an interesting problem, that's really just the very beginnings of a data science. That just tells you how to optimize. How do you get inference? How do you put this in the context of all these other problems I was talking about earlier? Huge interesting problems there if we really want to develop a real field. So let me finish with that last comment. Again, everything, as we said in all the rest of the talks here, have to do with data sets and curation and replicability and all those. Those are very much part of data science too. But I just want to reassure that people that are thinking, is this a mathematical field? This is fundamentally, deeply a mathematical field. And there's lots of not just math problems, but conceptual problems, which I currently believe we really have very little idea how to approach. And we're chipping away with them. And when we make a little dent in it, it's a lot of fun. But it's going to be a long, long road till we actually have a real field here. So thank you, everyone, for coming. Enjoyed giving the talk.